Hi, I'm Dr. A.J. Kumar, PhD. This is Abstract Algebra, I believe, 13, might be 14, might be 12, I'm not sure. So this originally started out as just a playlist where I was going to read this book, and then maybe intermix a few other books. But then, just to recap, before we kind of read through the first three chapters, they're very straightforward, very, anyone who has, I would say a high school level of math can understand the first three sections. And this fourth section, he has, the determinant is one of the most complicated things in mathematics. I think it's a candidate for the single most complicated and involved concept in mathematics, or the single most complicated and evolved idea, or involved. And in some sense, it's sort of it's not the most important, well, you could argue it's the most important function in math. I think that the exponential function is more important. But I've been putting off reading this chapter because I wanted to talk about some stuff with the determinant. Particularly, I wanted to talk about how you can use it to construct measures, because that's a really important that's a really important manifestation of the determinant. That's kind of the way you should, at least that's the way I'm preferring to think about it. And then we did that, and then I started talking about a bunch of other stuff, started talking about rational trigonometry, and that's going to be kind of important for later down the line. So before we get into reading this, I want to talk about why I'm reading this in the first place. Now, number one, abstract algebra is generally just an important topic, and it's always, good to learn about important topics. But also, my larger project is QAnal, which is my idea about how to fix analysis by getting rid of the CIA's limit psyop out of analysis. And the CIA has infiltrated abstract algebra a little bit, particularly through the sort of group of French scholars called the Bourbaki group, for which I think Artin's father was part. Michael Artin's father, Emil Artin, was part of the CIA's Bourbaki group. So the last chapter in this book, in particular, so QAnal is sort of split into two subfields, which is exanal and preanal. Exact analysis and precise analysis. QAnal is rational analysis, exact analysis, and precise analysis. Now, the main idea of analysis is here. So I got a new monitor, and we're gonna try. This is 4K recording, and so I haven't used the tablet on the big monitor, so I'm gonna have maybe a hard time adjusting. But so, where is just white? So we have QAnal. This is rational analysis. Exact analysis. And so this tree starts here and breaks into exact analysis. And I might change the way this schema works later, and precise analysis. So there's really nothing new over here. This is sort of old news. There is almost nothing new in exact analysis. This is stuff where you can compute something exactly, and there's really no ambiguity there, and it's just stuff that other people have thought of. This is sort of the new idea that I have, and by new I mean that I stole it from what's that guy's name? Lagrange. Am I thinking of Lagrange or Laplace? I always get them confused. Lagrange. Lagrange, this is the way Lagrange thought of calculus, and then the CIA covered it up. So this is basically Lagrange's formulation of calculus. I actually like the 4K better because it's denser resolution, and so I feel like I have an easier time writing. And then the CIA covered it up and replaced it with limits. So that's some math history. CIA replaced Lagrange with limits. Lagrange's calculus. With CIA limits. And so, but the point is that Lagrange's calculus was very algebraic. It's very similar to Wildberger's algebraic calculus. Wildberger is kind of maybe my main source for a lot of these ideas, and his main source is just looking at history and discarding the 20th century. Every idea, just as a general rule, irrespective of the domain or context, any idea that came out of the 20th century is a stupid idea, in general. There's a couple of exceptions, but pretty much the best idea that came out of the 20th century... Who the fuck is texting me? You know what, it doesn't matter, but I am wondering where my phone is, because it's not in my pocket. It's over here. Is it someone important? No, it's just Craig. Okay. Do not disturb for 2 hours. What was I saying? I don't know. But limits are a CIA psyop, so are infinite sets. And I want to decolonize mathematics away from the CIA's iron grip on the testicles of mathematics. I want to, let mathematicians be men again instead of emasculated CIA cattle. Anyway, but algebra is sort of the most important. We're going to be framing everything algebraically, and so having a strong grasp of algebra, which I do not have, is very important. And Wildberger in particular, on his Explore Research Math playlist, which is I think paywalled, has been sort of going after Galwa Theory. Now, Galwa Theory is in a sense the root of algebra. Algebra starts historically with Galwa Theory, really. Algebra is typically abstract algebra now is typically thought of as the study of groups, rings, and fields. Those are sort of the 3 fundamental abstractions. And Galois and Abel, really kind of at the same time, come up with this group idea. And for some reason, the CIA has put it as the last chapter of this book. And if you look into Galwa theory, it's based, you have to use Zorn's lemma, you have to use infinite sets. It sort of has I think the abstractions in Galwa theory are poor, and that was Wildberger's point, and he came up with sort of something closer to Lagrange's calculus as a way to get around the problems of Galwa theory. And I think it's very similar to WF algebra, which I went over on my WFC playlist, or in the podcast that's not in the WFC playlist because it's only on Altec. It's only on Rumble, and I think most of them made it to BitChute, but one of them is stuck in processing hell. I gotta downgrade the resolution and re-upload it, or maybe make the video shorter. I'm not sure. I will. Let me write down. You know what? Fix that. Anyway, we're going to learn algebra, or I'm going to learn algebra, and the way I'm going to learn, the best way to learn anything. This is a Scott Adams quote, I think. The best way to learn anything is to do it incorrectly in public. Or the fastest way to learn anything is to do it incorrectly in public. So I'm going to do algebra incorrectly in public, and then people will yell at me and tell me how stupid I am, and that's great because then I can be less stupid. But the goal here is not to give a perfect, clean description of algebra. It's to get the CIA's limit and infinite set psyops out of algebra so that we can free ourselves from the CIA's plantation. Escape the CIA's math plantation. Anyway, so without further ado, let's actually get to 1.4. And the arguments he makes kind of, very kind of CIA-like arguments here in 1.4, I think. Let me zoom out a bit. I also can't let these videos get too long because I was re-encoding the whatever video it was. I just published one earlier, the first one I did in 4K, and I have this, my processor normally can go through the video at 10x the speed, so if I have a 10-minute long video, it takes 1 minute on my computer to do all the processing. And now with the 4K, it's so much slower. Okay, anyway, here is 1.4. Let me just stop talking and read. Well, anyway, some of the reason that it's taken me so long to get here, number one, I wanted to rant about the CIA, but also I wanted to talk. The reason I did all those videos in the middle is I wanted to talk about the interpretation of the determinant as a way to construct measures, which is, in a sense, which in some sense I think is going to be fundamental to our way of understanding. Anyway, let's get started. Every square matrix A has a number associated to it called its determinant and denoted by determinant of A. I was editing the videos, and so I got the chair, but it's hard to speak with the chair, so let me stand up, then it's easier to talk. Every square matrix A has a number associated to it called its determinant and denoted by determinant of A. We define the determinant and derive some of its properties here. The determinant of a 1x1 matrix is equal to its single entry, right? Determinant of a 2x2 matrix is given by the formula AB, right? Determinant of a 2x2 matrix has a geometric interpretation. We talked about this. Left multiplication by A maps the space R2 of real two-dimensional column vectors to itself, and the area of the parallelogram. Right, there's a video I did in this playlist where I talked about this. The area of the parallelogram that forms the image of the unit square via this map is the absolute value of the determinant of A. Right. The determinant is a signed measure, which is better than a measure because it cancels, which allows us to do the thing where you can measure any shape and its translation invariant. Determinant is positive or negative according to whether the orientation of the square is preserved or reversed by the operation. I was framing this as clockwise versus counterclockwise. And then I also rambled about something similar in my Flappy Bird playlist, so you could go watch that. There was one video where I realized that the coordinate system was inverted, but the angle system wasn't, and I was just really steamed about that. And I went and rambled about the angles are another CIA psyop, by the way. Anyway, determinant of A is equal to 0 if and only if the parallelogram degenerates to a line segment or a point, which happens when the columns of the matrix are proportional. Right. So what this is saying, if we go over here, so we talked about how, so let me draw some axes, and let me draw two column vectors. Okay, and then we sort of, let me draw it in a way that constrains the angle. and that way it's easier for me to draw parallels. Okay, anyway, so it's measuring the, well, depending on the orientation, it's measuring the area of this parallelogram. Well, this parallelogram, the area will be 0 precisely when you have a situation, god damn it, where, you know, your vectors are like this, and then the other one is just a constant multiple of it. So that's what he means by the columns of the matrix are proportional. And since the determinant is invariant under the transpose operation, it also holds for rows. We're going to see that. Anyway, the area of the parallelogram that forms this image of the unit square, yeah, okay, where are we? Degenerates to a line segment or a point. Yeah, so we saw this. Let me change the color. Bright green. That's good. Oh. The controls are different in the journal program versus the painting program. Picture this operation in which the matrix is shown on the following page. The shaded region is the image of the unit square under the map. Its area is 10, which is 3 times 4 minus 2 times 1, which is the determinant of this matrix. God, I can't even see the pointer. Yeah, but it's 3 times 4 minus 2 times 1, which is 10. And, let's see. This geometric interpretation extends to higher dimensions, left multiplication by a 3 by 3 real matrix A, except, right, is the volume of the image of the unit cube. So I talked about this before. I talked about this. Go watch my sine simplicial measures video. I can't remember what it was called. It's previously in this playlist. Right. Here is the determinant of the matrix. Right, makes sense. The area of the parallelogram is 10. The set of all real n by n matrices forms a space of dimension n squared that, where is my pointer? There we are. That we denote by r n times n, or n by n. We regard the determinant of n by n matrices as a the real numbers are another CIA psyop. So keep that in mind. We regard the determinant of n by n matrices as a function from this space to the real numbers, right? Determinant from r n by n to r. The determinant of an n by n matrix is a function of its n squared entries. There is one such function for each positive integer n. Unfortunately, there are many formulas for these determinants, and all of them are complicated when n is large. Not only are the formulas complicated, but it may not be easy to show directly that two of them define the same function, okay? We use the following strategy. We choose one of the formulas and take it as our definition of the determinant. In that way, we are talking about a particular function. We show that our chosen function is the only one, by the way, by our he means the CIA, is the only one having certain special properties. Then to show that another formula defines the same determinant function, one needs only to check these properties for the other function. This is often not too difficult. We use a formula that computes the determinant of an n by n matrix in terms of certain n minus 1 by n minus 1 determinants by a process called expansion by minors. The determinants of the submatrices of the matrix are called minors, right? Expansion by minors allows us to give a recursive definition of the determinant. Right? We know what recursion is because this channel is all about Erlang, also, which are in functional programming. The word recursive means that the definition of the determinant for n by n matrices makes use of the determinant for n minus 1 by n minus 1 matrices. Since we have defined the determinant for 1 by 1 matrices, we will be able to use our recursive definition to compute 2 by 2 determinants. Then knowing this, right, compute 3 by 3 determinants and so on. let A be an n by n matrix and let Aij denote the n minus 1 by n minus 1 submatrix obtained by crossing out the ith row and jth column of A. Right? Right. For example, if A is equal to 103, 212, then A21 is, before I look, where is my pointer? So we cross out row 2, column 1. So we cross out this, and we would get 0351. Exactly. Okay. That makes sense? Expansion by minors in the first column is the formula. Right. This times the determinant of this plus this times the determinant of, or minus this times the determinant, right. So this notation, determinant of A is A11, determinant of A11 minus A21, determinant of A21, plus A31, determinant of A31, minus blah, 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 plus or minus, right, an alternating sign. This is called an alternating tensor, I think, is the, just remember this phrase. That's it. This is an important keyword to remember. The signs alternate beginning with plus. It is useful to write this expansion in summation notation, right? Determinant of A is the sum over nu of plus or minus nu 1 determinant of A sub nu 1. The alternating sign can be written as minus 1 to the power of nu plus 1. It will appear again. We will take this formula together with 1.4.1. What is 1.4.1? Right, determinant of a single entry. Okay. That is our recursive definition of the determinant. Okay. Where is my pointer? Here we are. For 1 by 1 and 2 by 2 matrices, this formula agrees with 1.4.1 and 1.4.2. The determinant of the 3 by 3 matrix A, shown above, is... Forgot to take some Mucinex. Sorry, gotta blow my nose. Determinant of A is 1 times the determinant of 1251 minus 2 times the determinant of 0351 plus 0 times the determinant of 0312 is equal to 1 times minus 9 minus 2 times minus 15 plus 0 times don't give a shit, and that is 9 minus 9 plus 30, which is minus 21. That makes sense. Expansions by minors on other columns and on rows, which we define in section 1.6, are among the other formulas for the determinant. Okay. It is important to know the many special properties satisfied by determinants. We present some of these properties here, deferring proofs to the end of the section. Right. Because we want to apply the discussion to other formulas, the properties will be stated. Okay, so this is where it gets really confusing, and I might stop the video here. So we covered the definition. That's important. And maybe I will cover the statements of these theorems. So let's look at the structure of his argument here, because it's a very complex structure, and I think there isn't any way to reduce it below this level of complexity and still be, quote, rigorous, unquote. I don't know what rigorous means, but... So, Theorem 1.4.7, uniqueness of the determinant. There is a unique function delta on the space of n by n matrices. I better be recording with the correct microphone. I am, thank God. With the properties below, namely the determinant. With I denoting the identity matrix, the determinant of I is equal to 1. Now, this is important when I was talking about the alternating tensors. So if you do differential geometry, there's okay, boy, I'm going to butcher this, but it's something like there is a space of tensors on a vector space, something like that, okay? Or k-tensors on a vector space. And the alternating tensors are a subset of those. The space of alternating tensors is one-dimensional, and the alternating tensors are all constant multiples of the determinant. The story goes something like that, and even if that's not quite right, it's close enough. And this first property is saying, the way to think about it is the space of alternating tensors is a line, like topologically it is a line, and it's saying, okay, well, these other two, I believe, are the properties of the other two properties of alternating tensors, which is linearity. That's definition of a tensor, and if two, so this I think is tensor, and this is the alternating property, or this is something equivalent to the alternating property. The alternating property would be that if you transpose two of the arguments in the tensor, then you think of you can think of the matrix as so an n by n matrix is n copy or n vectors. So it's a collection of n vectors. So the alternating property would be that if you swap two of the arguments, so if you swap two columns in the matrix, you get the negative, which when we where is this? So in our sort of geometric language, that would mean the alternating property would mean that, you know, if you swap, let me label these. Actually, no. So we would have a purple point. Let me go over here. So the alternating property here, it's easy to illustrate, which is that if you swap the two columns, blue and red, or green and red, then you would get the negative. And so that is, I guess, a consequence of that would be if you swap two of the rows and they're equal, you would get the negative, and the only number that equals its own negative is 0. So the second property is the tensor property, the third property is the alternating property, and the first property is which alternating tensor. This is the way I'm thinking about it. So the two properties 2 and 3 say that we're on this line, this one-dimensional vector space of alternating tensors, and then we say, okay, we fix which point we are on the line by saying, so, and they're all constant multiples of the determinant, and so we say, okay, well, if we know the determinant of the identity matrix, then given that it's an alternating tensor, we know what all of the other determinants are, if that makes sense. Okay. So linear in the rows of the matrix. What that means is that, well, it means this. Let's read his statement. The statement that delta is linear in the rows of a matrix means this. Let A sub I denote the ith row of a matrix. Let A, B, and D be three matrices, all of whose entries are equal except for those in the rows indexed by k. Suppose furthermore that D sub k equals C A sub k plus C prime B sub k for some scalars C and C prime. Then delta of D equals C times delta of A plus C prime delta of B. So you have a row here in this matrix, so this is D, and this is A, this is A, and this is B. And this is only on the rows. So we're not changing the entire matrix. This is a kind of a confusing looking formula. But what it's saying is, maybe we'll have an example. Yeah, he has an example here in a minute, so that'll clarify things. But what he's saying is that if one of the rows is a linear combination, then you can split up that linear combination, leave all of the other arguments intact, maybe think of the determinant as a function that takes n vectors. Instead of the matrix, remember I was saying think of the matrix as, so 4 by 4 matrix, think of that as 4 column vectors that are of height 4. Okay, what this is saying, and again the determinant is equal to its own, equal to the transpose of itself. It might be the conjugate transpose, something like that. If we're just working over rationals or quote reals unquote, reals are fake and imaginary numbers are real. That's the extent of the CIA's linguistic psyop, is that they've convinced you that fake numbers are real and real numbers are imaginary. Everything the CIA does is evil. Well, probably not everything. They probably do actually a lot of good stuff, but in math, their psyop has just been disastrous. It has ruined several generations of mathematicians. Anyway, what it means is you can split up a linear combination. That's what it means. In one of the arguments. So it's linear in each argument. So maybe another type of tensor is an inner product. And an inner product, we talked about this. So if I take the inner product of v and w, where v and w are vectors, this is another tensor. This is a type of tensor. This is probably not an alternating tensor because it's symmetric, and an alternating tensor is antisymmetric. But what this means is that in particular, so the way that this is defined, so if this is the inner product of v1, v2 against w1, w2, this is defined as v1, w1, I meant to do better ones, it doesn't matter, plus v2, w2. Well, if I take the inner product of c times v against w, something like that, sorry about the colors, this will go to, we're just getting a full rainbow display, aren't we? This will equal c times inner product v comma w. Right, and the way to see that is this would be cv1, cv2, so you get a c in both arguments here, and you can factor out the c. Okay, that's the linearity idea, and so this is another example of a linear tensor, is the inner product. The inner product is a linear tensor, and the determinant is also a linear tensor. It's just a more complicated linear tensor. And in sense, right. This is, right, but that's all it's saying, is that it's linear in each of its arguments. Okay? So, okay. This allows us to operate one row at a time, the other rows being left fixed. For example, since 023 equals 2 times 010 plus 3 times 001, okay, the determinant of this, right, so this is saying we've written this line, let me switch to a different, this color is fine. This line is our linear combination. So we write our vector as a linear combination, and then this is splitting up the linear combination. Okay. So, but you do that in one argument at a time. That's the point. Okay. So the determinant of this matrix over here has 2 rows. This second matrix, notice that it has 2 rows that are the same, and so by the property above, delta has the property that if 2 rows are the same, then the function is 0. So this would be 2 times, well, the determinant of the identity matrix is 1, so this is 2. Okay. I need a drink of water. Okay, and so I think, let's see, then he starts proving the theorems So I think I'm going to stop the video after reading the statements of the theorems, and then the next videos will go one proof at a time, because each of these is a really, really involved and detailed proof, and then seeing how the larger argument stitches together is also really non-trivial. So, the multiplicative property of the determinant. For any n by n matrices A and B, determinant of A times B is the determinant of A times the determinant of B. So, maybe a way to think about this, to convince yourself of this visually, is to go back to the parallelogram thing, which is the determinant tells you the scaling factor, if that makes sense. It tells you if you have, this is maybe a better way to think about the determinant, is that so let's draw a plane again. And let's draw two planes, actually. Okay. And you have any sort of blob region, and the area of this is x. And then you apply a matrix to it. So you have the vector maps to A times vector. Then the x will be some deformed shape over here. It won't look like this, but this is okay. I'm gonna use bad notation, but this is A times x, and by that I mean A applied to each value. X is, if you think of this as a set, x is a set. This is the set of A times little x, where little x is in big X, maybe. Anyway, the matrix will deform this shape, and so the area of AX will be the determinant of A times the original area of X. So maybe write it as signed area of AX will equal the determinant of A times the signed area of X in the original picture. Okay? And so if you just apply this recursively, then you get, and you pick a region where the signed area of X is 1, which is what he was saying with the unit square. The unit square, the thing about how the determinant is the area of the image of the unit square, that's a special case of this bigger property, which is the determinant tells you how the linear transformation scales areas, and the important feature is that it scales it does the same scale everywhere. Okay? It scales areas in a uniform way. And so that's the idea. Let's see. Signed area of AX is equal to the determinant of A times the signed area of X. Okay. Let's see. What else are we doing? The next theorem gives additional properties that are implied by those listed in 1.4.7. Theorem 1.4.10, let delta be a function on n by n matrices that has properties. Okay, so then I was just trying to give a brief argument, which is so you compose these two transformations. Well, the first one will scale any area by the determinant of B, and the second transformation will scale it by the determinant of A. Well, obviously, since the scaling is constant, you just multiply those two scaling factors, and that'll give you the scaling factor of the composition. So that's a way to think about it. Is determinant, that's another way to think about it, is the scaling factor for areas. And so right. All right. Let delta be a function on n by n matrices that has the properties 1.4.7, which is 1.4.7. Okay, that's our properties. So remember, key fact, this determinant, he means the specific thing he wrote down, and then he's going to prove that any function with these three properties equals the determinant. Okay? But this, and then so a consequence, any function with those three properties has this property as well. And then any function that has those three properties, namely the determinant, has all of these other properties. So it has this is our Gaussian elimination thing that I was talking about, which is that, remember when I gave you the exercise of taking the product, where you did Gaussian elimination, and you had some original matrix A, and you rewrote this as, Gauss n ... down to Gauss 2, Gauss 1 times the identity matrix. You could, if A was invertible, you could write it this way. And I'm working on code to demonstrate this. It's just got to get cleaned up a little bit, and I got to make some decisions about. And I have made my decision. It's just accepting it. What was I saying? Oh, well, I told you to take the product of the determinants of each of these and compare it with the determinant of A. And what this is saying, I think what this is saying is that the Gauss matrices that add a multiple of one row to another row, those have a determinant of 1. That's an equivalent of this. As long as you're not adding the row to the same. Okay. Right. So this is saying that the swapper matrix, so A is that the add one row to another row matrix has a determinant of 1. This is saying that the row swapper matrices have a determinant of -1. C is saying, if A prime, this is saying that the multiply the row by a scalar matrix is, these are more general statements, but I'm giving you some context. So this is for our, add multiple of one row. Let me just call this row adder. Where can I write it? Let me make the pointer smaller. This is saying row adder has determinant 1. Okay. Let me bigger pointer. This is saying that swapper has determinant -1. And let's use blue. This is saying that the scaling, the row scalars by C has determinant equal to C. That's what this is saying. And then a consequence of these three, this statement is equivalent to a square matrix has determinant 0 when it is not invertible. This is an equivalent statement. Or the conjunction of these three is equivalent to a square matrix has to 0 precisely when not invertible. That's the worst double arrow. Oh well. It is amazing how much better I am at writing with the drawing program than with this journal program. Anyway, so I'm not going to go through the proofs because the proofs are, well, I am going to go through the proofs, but in another video. I think let's just kind of look at the structure. So he proves 1.4.10 first. So he says, assume that there is a function with those complicated properties. Then he proves these statements for a function that has those properties. Doesn't matter which function. Then, oh boy. Then this is what I was saying just now, which is what those elementary matrices, those matrices that you use in the Gaussian elimination, that these are the determinants for them. I literally just said this. See, I'm the smartest mathematician who's ever lived. Anyway, that's what I was saying. 1.4.9. So this is saying that this is the multiplicative property, and he's showing this for any function that has the properties of 1.4.7, namely it's a alternating tensor that has a determinant equal to 1. A determinant of the identity matrix is 1. Any alternating tensor with that property. An example of an alternating tensor that does not have that property is our polygon, is our signed area of an edge thing, because remember that our signed area of an edge, I called this the signed area of an edge. So I said U V. This is 1/2 the determinant of U V. I'm being sloppy with my notation, but what I mean is clear. So in particular, this is an example of an alternating tensor that does not have determinant of the identity of 1, 0, 0, 1. This is 1/2 times the determinant of 1, 0, 0, god damn it, 1, which is equal to, I'm done changing the colors, this is equal to 1/2, which is obviously not equal to 1. Okay, but if you swap the rows, then you would get 1/2 times 0, 1, 1, 0, which is minus 1/2. So it is an alternating tensor, but it's not the determinant. The determinant is the only alternating tensor that has this property, that the determinant of the identity matrix is equal to 1. Let's see. So let me zoom out a bit. Sorry, just so it's easier to see. Sorry, maybe you're not able to read, but then I can kind of scan up and down. 1.4.7, so any alternating tensor, okay. What's 1.4? Okay. We're down here at the multiplicative property. He uses the prior results to establish the multiplicative property. Then the uniqueness of the determinant. And I don't know how he proves this, but then he says, okay, we have proven that any function that has the properties in 1.4.7, namely it's an alternating tensor that has the property that the determinant, that when applied to the identity matrix equals 1, then there is only one such function, and the determinant happens to equal that function, if that makes sense. That's what Theorem 1.4.7 is. What is corollary 1.4.15? Right. Corollary 1.4.15 is a square matrix A is invertible if and only if its determinant is different from 0. You can think about that as a consequence of the Gaussian elimination algorithm, which is that if you have any invertible matrix, it can be written as the... So he's developing this in a proper logical order, and I don't care about that really. I just want to understand what's going on. It's not that I don't care about a proper logical order, but I am, as long as one exists, I don't really care all that much what it is. A square matrix, that's not quite accurate. It's that you don't need to be super disciplined when you're just learning something. Right? When you're just learning something, you need to get the concept map in your head, and then later on you can figure out how to draw it from scratch. But what's important is learning the concept map. And then later on you can kind of start from the bottom. Anyway, I'm rambling. Anyway, right, these are consequences of the previous properties, probably from Gaussian elimination. 1.4.15. Determinant of a matrix A is equal to the determinant of its transpose. Now I am wondering, is there where is it? What is the analogous statement? What about complex matrices? Because I think I learned that at some point. I think it means the conjugate transpose, but maybe we can prove it. We can prove that. We can ask the question and try to have the tools to address it ourselves. That might be an interesting question. Right, so property C is a consequence of property B, which is that that if you interchange the words row and column, that's equivalent to doing the same thing to A transpose. All right. That's an outline of Artin's argument. It actually makes sense in a large scale as an argument, and then we're going to have to dive into the details of why each individual step is true. But, uh-oh. But that's good enough for one video. Thank you for watching, and thank you for listening to my rant. This video is way too long. It's going to take like 3 hours to encode. God. Anyway, thank you for watching. I will see you in the next video. Goodbye. Next video, we're going to go over the proofs. All right. Thank you. 51 minutes. Jesus. Okay. Stop recording. Bye.